Sabieh. So in today's session, I'll be giving you an overview of all the experiments that we do here in our single photon laboratory. This will be giving you the pure basics of whatever we do in the lab and also some of the advanced experiments and how those experiments will move on to some of even higher concepts that you'll be using in quantum information processing as well. Starting off, here is our team. So here was the core team who designed all the experiments firsthand, Dr. Sabieh, Hamza and the other team members who also contributed to the book that we have here. And then there's Abdullah who, and along with me, we are working on the current experiments that are being developed in the lab. So, starting off with the quantum world. How is that world any different from the classical world that we live in? The starting principle comes from the quantization of energy. So what does the quantization of energy says? If you have seen the atomic orbitals, so let's draw one. So for sodium, we know that there are a few orbitals or orbits in which the electrons can live. We know that there will be some electrons in the s level, and then there will be some electrons in the p level, d level, and so on. But we say that these electrons can't exist in the space in between. Why is that so? That is because of the quantization of energy. This shell has a specific energy associated with it. Let's say it's E1. And this shell has another associated energy. Let's say E2. Now, the quantization of energy says that an electron can have energy E1 or E2. But it can't have an energy in between these two levels. That is the basis of quantization of energy. But this quantization of energy takes a slight twist in the concept that's the superposition principle. Now all these things that we'll discuss in this slide will basically be how the quantum world is discrete or in somewhat shares some similarity, if it does, with the classical world. Now, one phenomenon that we see in the quantum world alone. Now we say that these are discrete energy levels, and the electron can exist in one level or the other, not in between these two. But we also give it a slight, what should I say, change of flavor. We say that an electron can exist between these two levels if we are not observing it. If we are not making a measurement, if we are not measuring what energy level is it in. So it could be in an energy level provided in some complicated system in which we are exciting or de-exciting these electrons. An electron could be, this is E1, E2. Now an electron could be existing here somewhere in this portion. But we won't know if it's there or not. If we try to measure it, we will find out that it is either in this state or in the other state. But statistical measures will show that it will sometimes take position 1 and sometimes will take position 2. Now this state of this electron, that it is occupying both of these levels simultaneously, and if we don't measure it, we don't know where it is. This position is called a superposition state. It is in both these states simultaneously, unless we measure it. If we make a measurement, it will turn out to be in one state or the other. By states, I refer to the energy levels. So here we have the energy states, and for this particular diagram I've drawn, we have 3 energy levels. All right, and then we have another interesting phenomena that happens only at the quantum scale, the quantum entanglement. We say that there is a particle, let me list you. There is a particle which has some quantum state of its own, and then we have another particle with a quantum state of its own. But we say that the two particles are entangled with one another. That means that at some point in time or space, they shared some physical phenomena that has entangled them both. And now, no matter what, if you take one particle to the other end of the universe or so, or let's just keep it to the solar system. If you take it to the other end of the solar system, these particles will still be sharing that same bond. Now, what sort of bond is it? This phenomena has entangled these two particles. A change in the state of this particle will correspond to a simultaneous change in the state of this particle as well. And this phenomena is called quantum entanglement, as said by Einstein, a spooky action at a distance. No, seemingly there is no physical contact between the two, and even no electromagnetic contact if you want to see it that way. But this action, that changing state of the quantum state of one particle changes the quantum state of the other. It happens instantaneously, faster than the speed of light, if I say. It takes no time whatsoever to see the action that has, of the changing of the state of this particle with that of the other. So this bond, if I am to draw it here, this is entanglement. Right now I'm just giving you the physical intuitive picture of how these things work. We will also come to the mathematical formulation of these things. Alright. Yes. And then there's interference. So interference we have seen it as a classical phenomena as well. But it turns out at the quantum scale the laws of interference still hold. Even if we have some particles that are going through, some quantum particles going through an interferometer, they'll still show the signs of interference. We'll go into details of that as well. And then there's the uncertainty principle. That if we, for a specific particle, a quantum particle, there is an associated, let's say, a position and a momentum for the two particles. Measuring the one will make us lose information about the other. And that's the Heisenberg uncertainty principle. Measurement, I've given you an overview of measurement right here. Yes. Here. So there was a superposition state, and the electron was residing in between these two states. But the act of measurement, as we can see here, these were the two states. And maybe the electron was somewhere here. But the act of measurement will collapse that state, and it will send it to one of these states that are available, the quantized states. And while doing so, we have also destroyed this state as well. Now, if there was a system, if I am to say, there was a system with these electron lying somewhere in between, and I made a measurement on this system. So this arrow here, right in the bottom, represents the time axis. You may want to see it that way. At some position in time, it was in a superposition state. I made a measurement on this. On this system. And now my act of measurement has destroyed this superposition state, and the new state of this electron will be either of the two levels, not in between. So if the electron lands right here. Now, there was a possibility that the electron would have landed in the other portion as well. But now that I've made a measurement, I've destroyed that state, and now no matter how many times I try to remeasure this state, now this state was measured right here, the state was destroyed, and if I want to remeasure this state, the outcome will be I'll find the electron always in this level, which it had occupied while I destroyed the state. So that's the act of measurement, destroying our superposition state and also giving us the information that is classical, that we can see, we can observe. Oh, here was also this interesting graph that I want to show you. So a colleague of mine performed this experiment a couple of months ago, I believe. And here is the spectrum of the light coming from the sky, and one time if it is like pointing towards the sun. Now we see that there are, it is hard to see, let me turn off the lights. It's fine. So, here in this graph, although this graph is somewhat smooth and there aren't any like major fluctuation, it is going through what should I say, a standard pattern, a rise and a low, somewhat like a Gaussian curve or something. But we see that there are some drastic dips here, aren't there? Why are these there? So the light from the sun has a whole spectrum to it, and it has a whole range of photons that are coming in. But while interacting with the particles in the atmosphere, so like as in we had sodium, and then we'll have other elements, other compounds as well that have some energy levels. And here's some electron in the ground energy level, let's say. The photons coming in to the atmosphere will interact with these molecules that are there in the atmosphere. And some of those photons, if their energy resonates with one of these energy level gaps, let's call these delta E. These electrons will absorb those photons and they'll excite to high energy level. And if there are a lot of molecules in our atmosphere, let's see, I think this dip, this drastic dip right here is for water. So apparently water is consuming or absorbing a large portion of the what was supposed to be this range of this wavelength of light that was coming into the atmosphere. So yeah, the quantization of the energy levels of water has absorbed this portion of light from the spectrum. Yes, please.
If we can't measure the particle in between the energy states, then how do we know it was there?
Statistics. So we won't be measuring this particle only once. We'll generate this state several hundred or thousands of times, and we'll repeat this experiment again and again and again.
But every time we'll find it somewhere else, not in
Yes.
between, but either in
Either of the two
one
states.
or-
Yes.
So
But
how the outcomes comes such that it is in between this?
So there will be some combination of in the statistics of your experiment. So let's say if you have seen, are you all familiar with the Dirac notation? So let's say if my this electron was in some superposition state of these two, it was a portion E1 and a portion of E2. Now in this superposition state, what is the probability that I'll get an electron in this state? 50-50. But what if my state was a different state? Let's say it was 1 over square root, what was it? Plus square root 3 over 2 of E2. Let me just rewrite this. What are the chances now that I'll land in the state E1? Any ideas? So for this state, the probability of landing here. Yes. So the probability of landing in the state E1 in this situation will be 1/4. So if I am to prepare 1,000 samples of this state and 1,000 samples of this state and perform the measurement on all of those samples, I'll see that for this state, if I am to say it's psi 1 and for this state psi 2, I'll see a different statistical outcome. I tried for it to be yes, square 1 over 4 or 3 over 4. Alright, so for that state, I'll see that the division of particles landing in state E1 or E2 will be in the ratio 1 ratio 4. No, 1 ratio 3. Yes. And for this state, the probability of getting one of these states will be half of the electrons will land in state E2 and half of those will land in E1. And by what should I say, reverse engineering those statistics, we can generate the state. We can make a guess of that state. Right? So there are experiments where we do guess the state for the single photon, and we'll get to it. Alright, so I think we're done with this slide. Any more questions? Yes, no. Let's move ahead. So this is a general overview of all the experimental setup. So here, this portion that is outside this dotted box here, this portion is the optical setup that we have. The detectors, the beam splitters, the crystals that will down convert, well, I'll get to that later, the crystals that are generating the single photons, it's all in this portion. And this portion right here is doing the signal calculation or signal processing for the outcomes of these detectors. And then we have the computer which will do the statistical analysis. In this lecture right now, we'll go into the depths of this optical setup and in this statistical setup. If time permits, I'll also touch a bit upon this signal processing part as well. So, for this experiment, we have a single, let's just first go to the outcomes of this setup and we'll go into the depths of the setups in the next slides. So we see that these counts are the single photon counts. And the probability of getting these counts in this range, that is around 300, is given by 0.025. And if I see, I think there is some in this data. I'll have a review of it and we can maybe see the other data in the next slides. So we are getting these peaks of the single photon counts. And while these counts here, that are the erroneous counts, if I must say, these are in the range of 1s or 2s. And on the other hand, the counts that are there on for the, what should I say, the classical light, that is not quantum, we're getting the photons or the counts in range of 1.5 times 10 to the power 4. So these are in the order of 10 to the power 4 as compared. So this is just like a number comparison of what the erroneous counts, the single photon counts, and the classical source counts are. Yes.
How do you actually generate a single photon crystal ke through what is experimentally happening?
Yes. And for that, I think it's in the next slide. So here, the slide that has content. I have to back myself. So this is the experimental setup. Let me just dim the lights a bit more. So this is the experimental setup as a whole, and in the next slides, I think we have the breakdown of the setup as well. So this portion right here, there is a laser, and then we have mirrors aligning that laser. There are some crystals in between that do something to the polarization of the light that's incoming. And then there is this crystal, BBO, the beta barium borate. And this crystal is responsible for generating the single photons. We'll get into the details of how is it converting, is it converting those incoming laser photons into single photons. And then after this, we have this nitrogen supply that's protecting that crystal. So this crystal is hydrophobic. If it gets moisture, a lot of moisture, it will be damaged, and it is quite expensive. We want to protect it, so we have a supply, continuous supply of nitrogen over it. And then we have the photon collection optics here. So here we have some beam splitters, some collimators, fiber optics that will collect those photons from this table and transport those photons using these fiber optics to these detectors right here. This is a detecting module that we have, and this is its 5-volt power supply. And after, so this was for this portion, if I remember. So this portion is mostly here. The detectors, the crystal that's converting, that's generating single photons for us, beam splitters and all. And in this next slide, here we have the signal processing module. So this is a schematic of the circuitry that's doing the signal processing for us. It's doing the coincidence counts. We'll get to those later for our detector count, the detected signals, and sending those over to a PC. And this here is the PC interface that we have. So it's created in Python using PySerial, so we use serial communication. And this is how we see the statistics in real time. Now we can also collect these stats and we can use those for further processing as well. This was just a very quick overview of the experimental setup. Now we see how is our crystal generating those single photons. So the process is called type 1 spontaneous parametric down conversion. Any questions? And explain how is it working. So this process is spontaneous, it's parametric, and it's down conversion. Let's first come to the part where the last portion of it, the down conversion. Why is it down conversion? The incoming photons that are being pumped by this laser to this crystal right here, I think I should do somewhere in between of this slide. Is it better now? So this pumping, if I am to say the laser that's pumping photons into this crystal is generating photons of the wavelength, or a laser beam of the wavelength of 4 or 5 nanometer. While these two photons, so this crystal takes in those photons of 4 or 5 nanometer and it converts those photons with some nonlinear process into photons, a couple of photons of 8-10 nanometer. So that's like half the energy of the incoming photons. Right?
What do you mean by nonlinear process?
We'll get to it. So it's not like we are performing some polarization changes, or we are like sending it through some beam splitter that's going to split it. So it's a different process. So what is that process? Yeah. And while the output are 2 photons of 8-10 nanometer, and this with the energy is conserved. We have 2 photons, but those are of half the energy and double the wavelength. The process of its generation. When these 4 or 5 nanometer photons are absorbed by the electron of this BBO crystal, so there was an electron here. It's a huge level electron for some reason, I don't know why. When it absorbs this photon, incoming photon of 4 or 5, it makes a jump into this level. But when it has to de-excite, it sees a couple of levels while coming down. When it comes down, let's draw this electron. When it comes down to this level, it will release a photon of 8-10 nanometer. And while making the next jump, it will again release a photon of 8-10 nanometer. So this is how we get those inequalities.
After you ask set the angle of the
Alright. So is it clear now how are we generating? So this process is a highly what should I say, low, it's a very low probability. So while having this process, we say this highly unlikely process we say that these photons that were generated in this de-excitation, we have marked an event. An event where two photons, only a couple of photons were released by this source. And if we are able to catch these two photons, it will give us a source or a quantum source. So how are we going to define a quantum source? So let me see, if we have to generate a source such that in our experimental setup, so there is this crystal, and then we have these collection optics right here, the detectors. So a single photon source would be one that generates photons in such a low quantity that while traversing through this setup, there are at max a single photon. Yes, there should not be more than one photon in this setup. So that's how we are generating the single photon source, if we are catching those photons, and I'll explain how we catch those photons. We have a single photon source if we can catch this event that's a highly unlikely event. So we are done with the down conversion point. I think you'll have a better understanding if I explain this term completely. And then this process is spontaneous. That means for an incoming photon, in those billions of photons that are being pumped by the laser beam into the crystal, for a particular photon, we don't know if it will down convert or not. That process is completely spontaneous, just like radioactivity. Alright, and we are done with the down conversion part, we are done with the spontaneous part, and we have another portion in this term, parametric. Why is this process parametric? So the thing is that this crystal, or DBO crystal, can down convert. So this process of generating photons of half the energy is called down converting. This crystal can down convert the photons if they are coming in with a specific polarization. Are you all familiar with the polarization of light? How it works? No? So polarization is defined by, so for electromagnetic field there is a direction of propagation. Electromagnetic wave. This is EM wave. So this is the direction of propagation, and this EM wave has an electric field and a magnetic field associated with it.
So like ये वाला तो process Raman scattering की वजह से you are relying on के Raman scattered photons आपके पास आएंगे, तो how are you screening the Rayleigh scattered photons?
I have to look into it. I don't have the it right now. I'll look into it. But for this down conversion, let me, yes, so I'll get to that portion as well. That after it's being output. So I don't know if these are those scattered photons. I'll look into it.
ये कि ये जो रिलीज फोटॉन्स होते हैं, I mean, you don't know ये किस डायरेक्शन में होंगे, रैंडम हो सकते हैं, तो you like place your detectors, मतलब उनको चेंज करके देखते हैं पोजीशन के जहाँ पे फोटॉन्स आ रहे हैं.
No, I'll get to it. That is a complex calculation that's being done while manufacturing that crystal. So a crystal has a lattice, a base, in which it is. No, it's not random. So it's being cut that way that it outputs those photons at a specific angle, and you can ask for that to the manufacturer that I want this material to output photons at this specific angle with the optical beam. So yeah, so this electromagnetic wave has an associated electric field and a magnetic field as well. So the direction of propagation of the electric field with respect to the direction of I should say the fluctuation or the variation of the electric field with respect to the direction of propagation of the wave is what we call the polarization of electromagnetic field. So if this is electric field portion of this electromagnetic wave, it will have a vertical polarization. like oscillating up and down with respect to the direction of propagation. So this is why it's vertically polarized light. But if it was oscillating in the horizontal plane, back and forth, so it's in the horizontal plane right now. I've tried to draw it that way, if it makes sense. So it's having a horizontal polarization. And for future reference, when I have the vertically polarized photon, I'll be denoting those photons with the state ket V, and with the horizontal polarization, I'll be giving them, assigning them a ket H state. Alright? And now, as I've explained, there is a manufacturing process in which we can specify the angle at which we want the VBO crystal to output the photon. We're done with that. Yes. So I think we should have a little exercise as well. And yes, the last part. Why is it type 1? Are there types of it? Turns out there are. So in the type 1 down conversion, if an input photon and we call this process, yeah, I was at the parametric part, and I had to move to the parameter that's monitoring this down conversion. So the parameter that's monitoring this down conversion is the polarization of light. So a specific crystal. All right. So a crystal will be able to down convert a specific polarization of light. If we have placed this crystal in the, let's say, the horizontal direction, it will be able to down convert the photons that are coming in the horizontal direction. And if we place it in the vertical direction, I'm just giving an intuitive picture of it, it's not like what's happening in depth. It will be able to down convert the photons. So these are vertical ones and these are horizontal ones. Now to make sure that whatever light we are inputting into our system, it gets down converted, we'll stack two of these crystals together. A horizontal, a vertical one and a horizontal one. So whatever our input state is, it will have a horizontal component and it will have a vertical component. These two crystals stacked orthogonally to one another will be able to down convert all of the incoming photons. And we have a photon source that can down convert all the incoming photons no matter what they are. And then comes the fun part. When the crystal down converts photons, this crystal, now I'm drawing this as a crystal stack. There are two crystals stacked together. If the incoming photon was in state ket H, the output state will be two photons that are in state ket V. And this is why it is the type 1 down conversion. In type 2 down conversion, we'll have one photon coming out in the ket H state and the other photon coming out in the ket V state. And the combined state of this system is ket V, ket V. Now, and it's the other way around as well. If the input was ket V, the output will be two photons of ket H and ket H. The output state will be, so H state maps onto H state maps onto state VV, and V state similarly maps onto state HH. Now, will you guys try it. Is there some space here or I have to erase it? I guess I have to. So this is how we generate different states of polarization or different states of how we generate different polarization states for a single photon. Right? So by changing the input state or to the BBO crystal, I can change the output that's coming, that's being down converted by the crystal. Now what if I would like you guys to try it if you have pen or pencil you are using to write. To this BBO crystal, I give a state that's neither H nor D, but a combination of the two. 1 over square root 2 at H plus at D. There is no phase in between, so we'll look it for now. What would be the output? Give it a try.
Next.
Using these simple phenomena. So an H state is converted to a BB state, which we can also write as at B instead with at B. And I want to down convert the input state that's neither of the two. It's a mixture. Yes?
Thanks for that.
So let's just let them try it for once. So I think you're done, right? So if the state passes through the BBO crystal, this portion will be down converted as it was being down converted before, and so will be this portion. And what we'll have is 1 over square root 2 right here, and this H state will get down converted into state BB plus state H. Is this state familiar? Ringing any bells? It's the best. This is how we generate entangled photons in our system. Like this is just a simplified picture of it. There is some phase associated between the two components of light because these crystals have a finite distance between them, and that causes a phase difference between the two. To nullify that phase, we have to insert a quartz plate here that can provide a counter phase to nullify that process. Alright, so I think we are good to go to the next slide. I think I'm taking a lot of time. How much time do we have left? Right. Any questions? Here. So, we have a light, we have photons, and we have to deal with those. So, you would have seen that there are gates that we apply in the quantum channels that change the polarization, that change the state somehow. If we have the state that if we had a state 0 and we applied a NOT gate on it, what will be the output? A state in 1. Now this is very convenient to do in Cascade. You just apply the NOT gate and it does that. But how are you going to change the state of a photon? That's a particle of light. That's basically light, and you have to first assign 2 levels to it. So the 2 levels that we are operating on are not bits, but there are not zeros or ones as those are in the Cascade circuitry. we are using the cat H and cat V states. I think I did mention it somewhere. Yes. The cat V and the cat H states will be our basis states, if I am to say, instead of zeros or ones. Now if I want to convert a photon in cat H state to a photon in cat V state, I have a photon in cat H state, I want to convert it into a photon through some process into cat H state, or cat V state, sorry. I'll need to change its polarization. To do that, we have some special materials that are known as birefringent materials. Have you heard of those materials? What are those materials? Anyone, any answers from me? What are birefringent materials?
जिनके refractive indexes जज करते हैं change
that have more than one refractive index is provided with what input polarization we are going to that giving to that material. So if there was a birefringent material, it would have a fast axis and a slow axis. And if I had to give it an input polarization light and it had both a horizontal and a vertical component, both those components will see a different refractive index, and because of that they'll travel at a different speed in those materials. And if this material has a finite length, after passing through this material, the input polarization, it has a vertical component and it also has a horizontal component. After passing through this material with birefringent material, one of these polarizations or the portion of light that's these two polarizations will have a phase difference between two, because one portion of the light was traveling at a different speed than the other portion. Now this portion, if it's being displaced, will give us a different combination of H and V's, and this will be a different polarization of light. So this is how we change the polarization. Now the polarization changing elements are half-wave plates and quarter-wave plates. Why are they named so? Half-wave plates and quarter-wave plates. As the name suggests, a half-wave plate will introduce a phase difference of half the wavelength. And a quarter-wave plate will be giving a phase difference of
90 degrees.
Yes, or if I can say 1/4 of the phase difference. This is how I manipulate my polarization of photons. This also works for classical light, it will work for the quantum light as well. So these are basic matrices that give us general matrices that can give us the if I am to write this state cat H as 1 0 and cat V as 0 1, multiplying these vectors, these state vectors, with these matrices, which are basically operators, the observables as we say. So these observables, I think it should have been taught to us in a different way, that there are some things that we can observe, and the matrices corresponding to those things are called the observables or unitary operators. So those are the unitary matrices that give us the mathematical formulation, or the mathematical, I should say, the maths behind the evolution of those states. So multiplying those matrices with these states will give us the output that is to come from after passing through these birefringent materials. There are 3 of those. One is for the linear polarizer, one is for the half-wave plate, and one is for the quarter-wave plate. I can go into the depths of how do we generate these with some specific angles, but I think that will take a lot of time. Let's just leave that.
This crystal does not make ये जो horizontal polarization है, vertical में तो change नहीं हो रही, इधर बस इनका थोड़ा सा आपस में phase difference भी आपको change हो रहा है.
फिलहाल But if we have a polarization that's completely horizontal, and if I tilt this material at some angle, so let's say if this fast axis and the slow axis were not at these parallel to the vertical and parallel to the horizontal, but they were at some angle. Let's say this angle here is 45. Now this portion, so this is like changing my basis, if I am to say, or changing the reference frame. Now this horizontal polarization will have a component that's parallel to this portion and a component that's parallel to this, the fast axis and the slow axis. And after passing through this, if we have a significant or appropriate phase angle, which I think will be half the wavelength in this case, the output will be the vertical polarization. Let's just move on ahead. I think you guys are bored. Are you guys okay with the space or? So, at the measurement part, so here we had the state generation part. First we generated the state, we saw how the state will change depending on the input what we are giving it to the crystal, and then we saw that how can we change the polarization of light. These matrices will be applicable to both the incoming beam, the laser beam or 4 or 5 nanometers, and single photon light beam. And now for the detection. For the detection, we say that there are some different bases of measurement. There are 3 sets of bases, the horizontal, vertical, and if I am to draw these on the block sphere, I destroyed the states and there was no word left. Alright, so on the block sphere, not a very cute block sphere, but that's it. So here is, if my state H, the orthogonal state corresponding to it will be cat V. If here is my state cat D, which basically is the state which is half of both and this state will be cat A, the anti-diagonal. So that was diagonal and this will be the anti-diagonal, and the sign will only change for this state. Similarly, this state right here will be cat L, so this corresponds to the circular polarized light, and this R is with the opposite phase, the circular polarized light. So it's right circular and it's left circular polarized light. And it turns out changing the input basis is how we, should I say, most of our statistics or most of the analysis depends on these bases changing. So if I had polarizer, a polarizing beam splitter, and I sent in a state H to it, it will let this state pass through. And if I had the state at V, it will reflect it. But what if I had cat D coming into this polarizing splitter?
D कौन सी होगी
This
mixed है तो आधी पास कर देगी आधी डाइवर्ट हो जाएगी
half probability of it for it to pass through and half for it to go straight ahead. This way, if we had a state cat D and we wanted, and I want to change my measurement basis into such that it detects D, it will not split it into two. I will have to add a half wave plate before this D splitter. Right? So if I have this half wave plate at 45 degrees, or no, it should be 22.5. There is that table. Yes, it is here. So for the DA basis, I'll have to. It's a bit like I get it. There's this mumble jumble between these numbers. So for this state, so I have verified these states here. I'll have to add a half wave plate after the state passes through a quarter wave plate. This should be at 45 degrees and this should be at 22.5 degrees. And it turns out if I send a depolarized photon through this system, it will get straight through. And similarly, if I have a V-polarized photon passing through this system, it will be reflected. Just like it was doing to the H and B bases. And I've changed my system into a different measurement basis. These measurement bases will come in handy for these experiments very often. Right. Now, once we have detected these photons, so how are we going to detect these? We have collected these photons using the fiber optics and all that we were discussing. I should be moving to that side. So we had, so these D's I was drawing at the end, I was saying these were detected, right? There were these photons coming in. This was our crystal, and then we had this thing and this thing. Turns out this is just a portion of our detecting system. So these I represent here are the collection optics. These will collect those photons and transfer those photons into fiber optics. These fiber optics will transfer these photons to our avalanche photodiodes, which was that device in the starting of the experimental setup where they were the experimental setup was with power supplies and everything. Avalanche photodiodes. These diodes, when detect these photons, will generate an electrical pulse in response to the detection. And these pulses are what we have after passing through this optical setup. Now, what was our play with photons and light has turned into a play with electrical signals. These signals are for a signal detection. This detector will generate a signal of around 15 nanosecond width and 2.2 volt into peak. And this signal will be sent into the coincidence counting unit, the CCU here. So this portion is being implemented here. The portion that I said I'll go into the detail if I have time, which I definitely won't. So yes, so this will count these pulses coming in per second, and it will also see if these pulses coming together at these events. One important thing about the single photon detection. If I say that those photons were generated in that same event, I have to prove it that those were generated in that same event, and those are not some random photons coming in that I'm counting. For that, what I'll do is that whenever I detect a photon on one of these channels, I'll start a timer of 20 nanoseconds, around 20 nanoseconds. And if in that time window I find the other photon, which is like a very narrow window, and it's highly unlikely that a photon that was not generated at the same time and was traveling the same trajectory as the other photon, or the counter, or should I say the corresponding trajectory at the other 3 degree angle, we won't get a detection. But if we are getting those detections, we say that this is that event that generated those single photons at the same instant. And by catching that event, we say that we have the single photon source. We are catching the event, the highly unlikely event that's sending in a very few photons one at a time, if I must say, through this setup. And once we have those photons coming in that can just pass through one at a time, we say that this is our single photon source. And we can manipulate and we can play with that source to find our statistics and whatever we want to do with it, and even whatever. So it means that that event that we were using to generate the single photon, say yes, that one. No, it's not that one. The one in which we were down converting, we were getting 2 photons of half the energy. Remember? So those 2 photons were generated instantly at the very same instant, and that's why those photons were entangled somehow as well. We can get into detail when we get to the entanglement part as well. So it's long presentation slide. Alright, so that highly unlikely event that was instantaneous when those 2 photons of 8-10 nanometer, which is also a highly unlikely event, and those 2 photons being generated at the same time, and for us to catch that event will be that we are catching that event, that highly unlikely event, and those photons are a single photon source now. Yeah? Where were we? Yes, that's basically it. So this is why this detection is also called heralded single photon detection. One detection heralds. So herald is basically the person who delivers news in old times. So there were those people, when there was a news, they would pick up their drum and they would go into the market to show or to give the message of the king to the public. So this is that herald. So whenever it detects a single photon, some photon, it will herald the incoming of the other photon. It will say that, yeah, I am here, so there might be my brother coming to the other end. Detect him, please. So if his brother comes to the other end and in that small time window, we have detected our highly unlikely event. Seconds. Right. I think we should go ahead. And after those are counted by the CCU, the counts or the statistics are transferred to the PC. Finally, to the first experiment. Now we have that photon source, and we want to show that this source are really single photons and not some light that we are detecting and we are saying, oh, we have some detection and these are single photons. So I think this is a fun experiment. Coming back to our beam splitter part. So a polarizing beam splitter will split the incoming light with respect to the incoming polarization of that light. If it was horizontal, it will be transmitted straight through. If it was vertical, it will be transmitted, reflected. So if I had a state half, sorry. H plus B, we saw that half of them will be, or if I say if it was intensity I naught, so the intensity that we are getting in this arm will be half I naught, and the intensity in this arm will be half I naught as well. Agreed? So here we were talking about intensity. But what if I have a single photon coming in with the same input polarization? How will it interact with this beam splitter? Any ideas? Will it split a single photon? What will it do then? It will either get reflected or get transmitted. probability half. Now I can't write intensity in this case because for intensity I have to have a large number of those photons. And probability half, it will be taking this form. Now we have this beautiful formulation right here, the G2O. There is a whole lot of derivation behind it and we're just looking at this formula right now. Now if we had these intensity patterns that we saw that happens with classical light, this is the classical case. An incoming light would pass through the beam splitter if it had this polarization, and it will give a detection on both these channels simultaneously. And in that case, we'll have detections, but we know that for quantum particles, that particle can take only one of the two path angles, right? So this detection, here, it can either be on this channel, the reflected one, or the transmitted one. It can never happen at the two detectors simultaneously. And so if I have to give names to these detectors and paths, it will make our lives easier. So this here was some source. I should go ahead with that as well. I think we'll just do this experiment and we'll wrap it up for today. So here are the two arms that we had, and here I should name them A and B, and one is heralding the detection of the other. And in those same paths, so I say that when both the photons come in at the same time, I say that there's a single photon detection event. So that counts at A and B simultaneously. There will be the coincidence detection AB finally. Right? So a photon coming in at detector A and detector B is termed as the coincidence AB. And what if I am to split this detection system? So now this B is here, and I have added another detector, that's B prime. Similarly, here I have, let's just keep it to one channel for now. I have added a beam splitter in one of these channels, and in one is this A, the old one, and the A prime. Now, I'll use this detector, the B that is gathering all those photons, as the herald. So if it gets a photon, it will say that we are going to have another photon on the other channel. So similarly, for the coincidences on this detector and this detector, we'll get coincidences AB, and for the coincidence on these two detectors, we'll get A prime B. Right? I could have named them the other way. I could have named them B or B prime and A here, and we'll land into this expression. So it says that, what do you think should be the probability of this event? That a photon gets detected on detector A, or this one, the herald, and on both of these at the same time, on all three detectors click at the same time. Is this likely event? No. So this formula right here gives us this very nice and neat interpretation of all the system. If we run this statistical test on these photons, the numbers that we get, you see that this numerator will be a very, very, very small number, and it will always be some, what students, it's an accidental event if these two, if this count ever happens. And similarly, this event will be likely event. So half of the time you will get this probability, and half of the time you will get this. So this P is representing the probability, and there should be zero probability of getting a photon here. So if we have a quantum light that we say that the photon cannot go through both the paths at once, this whole factor G2O should go to 0. Similarly, if we had a classical light, so there were at that time people who said that light is classical, there is no way that you have a quantum source. There were some people like who were going against the idea that you do not have a single photon source and you're just making a bluff. So for that, we see that if their claim was right and there were a splitting of those photons, so this value should have been closer to 1. Right? So for our test that we ran in the lab, we got this value 0.08 with a very low standard deviation. And hence we prove that this photon source that we have is truly a quantum single photon source. There are only a few photons coming in at the same time, and at a time only one photon passes through the center. Right? I think we should call it a day for now. Or you want to learn more?
ये नोमिनेटर वाला फैक्टर को नोट देना कैसे हो सकता है?
डिनोमिनेटर वाला
नोमिनेटर
एक्सीडेंटल काम हो सकता है कि वो